Hello, everyone. It's very nice being here at Hack.lu again. And as Klaus mentioned, this idea actually came to us after a bit too many beers here in the bar. So it's kind of a closure for us to present it over here. Let's begin. So first of all, this is us. My name is Yaniv, Balmas, and I am a security researcher, and I work at Checkpoint, and so is Eyal Itkin, my colleague here. And let's dive right into it. But just a bit about fax history before we begin. So it all started at 1846, when a scientist named Alexander Bain invented or managed to send the first image of a wire. And fun fact, this happened around 20 years before the invention of the light bulb. And then it continued, and that was the first something that looks like a fax machine that we know today, again, around 20 years before the invention of the telephone. So humanity was sending fax before we actually made phone calls. And then some more advance in fax, and mainly the main ones is in 1966, a very small and unknown company called Xerox made the first commercial fax machine. That's the commercial there. And then at 1980, an organization called ITU invented the de facto standards for fax, namely T30, T4, and T6, which is basically the same standards and the same protocols that we still use today, with slight modifications. And now, this was all in the past, right? But today, I mean, we have better ways to send electronic documents from one to the other, right? Let's try to compare fax to just one of them. On the top of my mind, email, for example. So just to remind you, we are comparing this to this, right? So in terms of quality, yes, I guess, you just saw those pictures. I have nothing more to add. In terms of accessibility, I'm pretty sure most of you here or all of you have 24/7 access to email. I'm not so sure you're carrying around your fax machines with you. Regarding reliability, when you send an email, you know that it gets sent or not sent to, or received or not received by its destination. But, for fax, we have nothing. So yes, we have this paper saying received okay, right? But, if there's no papers in the receiving printer, for example, you will still get this. If the dog ate it, still absolutely no reliability in fax, right? And regarding authenticity, well, we can argue whether or not email is authenticated, but we do have public key cryptography, and stuff like that helps us with that. What we don't have is we have nothing for fax, basically, right? Absolutely no authenticity. So looking at this table, one might think, okay, so fax did its job, right? It was really good in the past, but obviously nobody is using fax today, right? Wrong. Everybody is using fax today. It's being used everywhere. Ships, maritime, at open seas, receive these critical telemetry maps using fax over radio. Japan, according to Wikipedia, at least 90% of the Japanese population use fax. They really love fax in Japan. That's all I have to say about that. And if you do a simple Google combo search like contact us and fax, you will find around 380 million fax numbers published on Google. And that's only the published numbers. Think about how many numbers are not published. It's absolutely mind-blowing. And, it's not only about how many fax machines are out there, but it's also about who is using fax. And the thing is that everybody is using fax. If you're a small company, medium company, a huge corporate, you have a fax number. You don't necessarily receive any faxes over this number, but you do have a fax number, and there's a fax machine standing behind this number. And now we're in Luxembourg, right? So if you're a bank, you really love fax. And this is Bank of China, the biggest bank in the world, and this is his fax number. And I think last but not least is that if you're a government institution, you wake up in the morning and you want fax. That's what you want. And this is the fax for Donald Trump, if anybody ever wants to send a fax to the White House. So it's just there. We just Googled it. And we find it to be very funny. And the thing is that I think mostly banks and government institutions, they don't only allow you to send fax, but a lot of times it's actually mandatory to send fax. There is no other way. You can either use postal mail or fax. That's it. They haven't heard about any other option. It happens a lot all around the world. And we were thinking of this actually here in the bar, as I said, in Luxembourg. And we said, what the fax? How is it possible? We live in 2018 and we still use this 30, 40-year-old technology. There must be something that can be done about this catastrophic behavior, and that's what we started doing. And just before we tell you what we did, so I have to explain how does fax looks like today. Well, today, fax is not the same thing that we had 30 years ago. 30 years ago, we had these standalone fax machines, right? And they were doing fax and only fax. But that's kind of not the situation today. Today, fax is, most of the times, it's like a 30 years old technology wrapped around like newer technologies. So, for example, we have fax to email or email to fax. We have fax over radio and fax over satellite. And I think most commonly, we have this kind of these creatures there, these printers, these all-in-one printers, right? I mean, you see them everywhere in organization, in homes. There are like millions of these around the world. And our research actually focused on those devices, the all-in-one printers. And I mean, if you take a look at those devices from a security point of view, then you can consider them to be black boxes, right? And on one side of this, they have interfaces like Ethernet, Bluetooth, Wi-Fi, stuff like that. And those interfaces connects the printer basically to the world, right? To the internal network, the external network, and everywhere else. And then on the other side of this black box, there's this nice little interface that connects us to, well, somewhere to 1970, I would say, of course, to the phone line. And the thing is that if you remember that these devices, at the end of the day, they are nothing but computers. You see, they have CPUs, they have memories, they have operating systems. Basically, it's a computer, right? And we were thinking to ourselves, okay, so what would happen if an attacker sitting somewhere in the world with access only to the phone line and equipped with its target's fax number, what will happen if this guy will be able to send a malicious fax, right? And then take over the printer using this fax. If he'll be able to do that, he can then propagate and pivot from there through any of these other interfaces, let's say the Ethernet, to the internal network, right? Because this thing is connected both ways. And effectively creating kind of a bridge between the internal network and the external network, just using the telephone line. We're back to the 1980s again. So we thought that this would be really, really cool, and we accepted the challenge and went for it. So then after we got excited a bit, we sat down and talked about this, and it turns out that we have a lot of challenges ahead, let's call it like that. Really a lot of challenges, and most of them look, at least, or they sound really, really hard. And let me just give you some of them, you know. So first, we have to understand how to obtain the firmware of the printer. We need to read the code of this somehow. And then after we did that, how do we analyze this firmware? And what is this thing even doing? What operating system is this thing running? We have no idea when we start this thing. And then how can we debug this thing? It's a printer. How the hell do you debug a printer? And then how does fax even work? We know the beeping sounds, but we have no idea how it works. And after we did all that, then we can start discussing about where we can find vulnerabilities and how we can find the vulnerabilities. And today in this talk, we're going to take you through these challenges one by one, as best as we can, until we'll be able to do exactly what we wanted to do. So first challenge, how to obtain the firmware. So before we tell you how to obtain the firmware, let me show you, this is the very poor printer that we abused for so much time. And it's an HP printer, it's an HP OfficeJet printer. We chose HP basically not because we dislike HP, but because they have around 40% of the market share. So they're just the biggest target out there. And this specific model, well, you know, I can say a lot of things about why we chose this model, but practically it's the cheapest one. So yeah, we could afford buying like 3 or 4 of those and just break them. And now we wanted to break fax, but just a second before we break fax, we need to break the printer. And I mean literally break the printer. So that's the fun part of the research. We take everything open and take it out and start looking at that, and then we start mapping what we see. So that's the main PCB. That's the brain behind the printer, right? And it has several components on it, like flash ROM and SRAM, and it might look like not enough components for a PCB of a printer, and that's because this thing has 2 sides to it. And on this side, there's all the interesting stuff like USB, Wi-Fi, electricity, some kind of strange battery that's used for something, and SRAM, and specifically 2 very interesting components. One is the CPU. This is a CPU manufactured by Marvell, and it's manufactured specifically for HP. So you can't get this thing on AliExpress or Alibaba or wherever. Only HP has access to this thing. And the other component is this one, and it's a fax modem, right? And what's interesting to us is specifically what's going on inside those components and the connection and the relationship between them. And that will be our focus. And as I said, our main challenge, at least at the beginning, is to get the firmware of this thing. And when we are taking a closer look at this PCB, we find two very promising interfaces. One of them is called JTAG, and another is called serial debug. It's really clearly marked on the PCB. And now we say, okay, so it's going to be really easy. You know, there's a JTAG here. It will give us like read access to the memory, write access to memory. And basically, that's all we need. But it turns out that it's not going to be that easy, you see, because the JTAG is completely disabled. Of course, it's disabled on the manufacturing line, so we can't access it. And the serial debug, well, you know, we managed to connect to it, but what we get is this, like a terminal. But almost every command that we try, we get this like error, I don't understand, and we don't understand either. What should we do now? So obviously, it's not the right path to go, and we need to find like an alternative path for that. And luckily for us, we browse the internet, and we find this wonderful, wonderful site, FTP site online. It's HP's FTP site, and this thing contains every firmware version for every HP product ever produced in the history of HP and the humanity. This thing is so huge. It took us like about 2 weeks to find our firmware inside this thing. Yeah, but feel free to go and find, there's other stuff other than firmware. I think it's really nice. And now, okay, so we got our file. This is like the firmware upgrade file, and now we need to make sense out of it because it's not an executable. It's something we need to understand. Basically, how do we upgrade the printer's firmware? And I mean, I have no idea. I've never done that before. And how do you even do that? And it turns out that the answer to this question is surprisingly funny. Well, you just print it. It turns out that the printer accepts firmware upgrades just the same way as it accepts print jobs. You see, HP defined this nice document called PCL XL Feature Reference Protocol Class 2.1 Supplement, that if you are still sane after reading this thing, you understand that HP defined something called a PJL, print job language, that over this protocol you send both print jobs and upgrades, and our file really is consistent with that, because you see it starts with this like PJL, print job language thing. So, okay, that's what we're looking at, and now we kind of need to start opening this thing. It's like an onion, and it has layers, and we need to start opening those layers one by one. And there's a lot of work here, tedious work, really not interesting. I'll just tell you that the first part of it is composed of a lot of decoders. Like there's something called a null decoder, TIFF decoder, delta row decoder. Really not interesting, but the main concept is like saying something like, okay, if the previous line was all spaces, then if this line is also all spaces, just write one instead of the line. Compression, right? Now, this makes perfect sense when you are sending a print job, because, you know, like print papers have a lot of spaces in them, but when you're sending a binary file, it makes absolutely no sense. It's completely useless, but still they do it. And we found it pretty funny. And, you know, we said to ourselves that when you're a hammer, everything looks like a nail, right? So when you're a printer, everything looks like a print job, and the firmware as well. We found it a bit funny. And okay, so we managed to, you know, peel off all these pieces, and now we have a file which looks like the firmware. And now we need to start analyzing it. And just when we start analyzing it, right at the beginning of the file, we find something that looks like a table. And we define it in IDA, and it really is a table. Turns out it really is a table. And this is something called a section table. Basically, this big file that we got now is composed of several sections. And this table just explains those sections. So it states the loading address, the section name, and then the location in binary. So we can now take this file, split it into several sections, and inspect each and every section. One of these sections, specifically, I think it was the biggest one, is the one that's interesting to us. And it's interesting to us because we kind of understand that we're looking at the firmware itself. And how do we understand it? I mean, those are just snippets from this section. And take a look at this. Yeah, error, I don't understand. So we are looking at the same serial protocols. That's the code. That's what we're looking for. But it's not completely there. Something is missing. You see, there are some letters missing there. And those bytes are consistently missing from the entire firmware file. So although we know that we are there, we are still not completely there. We need to find were these bytes replaced with in order for us to read the firmware. And that's a pretty big challenge. Now, first, we need to understand what is this thing? Why are those bytes missing? And we have a lot of assumptions here. All of them are crazy, completely crazy. But I think that the least craziest assumption would be that this is, again, another form of compression. Why? I have no idea, but it's a printer, so I'm not asking a lot of questions. But the thing is that if this is a compression, it's really a bad compression. Because when we take zlib, for example, and compress the same thing with zlib, like the most standard compression algorithm out there, so we get about around 80% better compression. And we know that the printer has zlib because we can see the strings for zlib in it. So why won't they use zlib? I don't know, but still we need to do something with it. So let's take you through this challenge and how to decode this crazy compression algorithm. So this is the snippet that you just saw a minute ago, and let's try to decompress this together. So that's what we have here. Basically, it's composed of two types of characters. One is ASCII characters, stuff that we can read, right? And the other part is stuff that we can't read, non-ASCII characters, right? And if you take a look at this byte map here, then you take off all the ASCII characters. Those are our missing bytes, basically, right? And if you stir this long enough, you will start seeing a pattern. And let me make it a bit clearer for you. You see there's this one single bytes there, and then there's double, like 2 bytes, double bytes, right? And the distance between the single bytes looks, I would say, suspiciously patternish, like 8 bytes, 9 bytes, 9 bytes, 8 bytes. But what does it mean? I mean, if you take a look at this from a different perspective, maybe the pattern will start being a bit clearer. You see, the F7 and the F7, they look the same. The FF and the FF, they look the same, right? Now, what does it mean? Well, in order to answer this question, you need to sharpen your binary view a bit. And if you understand that FF is just 8 1 bits, right? And if you do this consistently for all of these things, then you will see the pattern. And the pattern is that the 0 bit always falls in the 2 bytes hole. So that's perfect, because that kind of means that the first byte that we see is just a bitmap, like describing the following 8 bytes. Wherever we have a 0 bit, there was a replacement. The replacement is 2 bytes long. That's perfect. Now we know what this 1 byte is. And all we need to do is to understand those 2 bytes and what were they replaced with, right? And in order to do that, if you know anything about compression, you know that there's not a lot of options here. It could be a forward or a backward pointer. It could be a dictionary, or it could be a sliding window. Now, we know it's not a forward, backward pointer, and we know it's not a dictionary, because we try to reference it in our firmware to stuff that we know that should be there, and we can't. So we ruled it out, and then we're left with a sliding window. So that's probably what this thing is. And once we have this information, we go to the internet and start looking for something that looks similar to this. And in some very, very, very dark corner of the internet, we find this nice site here. Something describing a soft disk library format. So have you anybody heard about this company, Soft Disk? You probably have, but you forgot. That's because we found here a compression algorithm that looks exactly like our compression, exactly, bit by bit. And we found it really funny because this company, Soft Disk, actually developed this algorithm somewhere in the 1980s. And it wasn't used, I think, maybe, at least I haven't seen it used anywhere since, but it's still used in HP printers. And you have any guesses where was this thing? What is Soft Disk and where was this thing invented? For what? Yes, it was a compression. It was a compression for Commander Keen, the famous computer game. So yeah, that's the guys who invented it. And how did this thing get into HP printers? I have no idea. I have a lot of speculations, but I have no idea. But it did. And now every HP printer is running a part of Commander Keen in it. So yeah, that's pretty funny. And once we understand this sliding window thing, so now we have all the information that we need in order to actually decompress this thing. And basically, it's like we know that these 2 bytes are composed of 2 values. One is window location and the other is data length, and that's basically what we need. And let me give you an example. So what we have is an output text, an input text, and a sliding window. And let's try to compress this string here together right now, okay? So the first byte, it's a bitmap, so we don't know what the value will be. We just leave it open for now. And then we start with A. So A we write both in the output text and in the sliding window, right? And then B, and then C, and then D, and then we get to A again. But A is already present in the sliding window, so we don't need to write it. And then B is just the character following, right? And then when we get to E, we write 0, 0, 0, 2. That means go to the sliding window at position 0 and take the first 2 bytes. That's the replacement. And then we go on, E, F, G, right? And now once we have that, we have our bitmap, and we know that the value here should be EF, and that's basically it. It's consistent. You can decompress the entire firmware using this thing. It looks really easy when you look at it that way, right? But backwards is kind of a bit more complex. Okay, so now we open this thing, we have a full firmware at least, and now we can start analyzing this firmware. It took us actually a lot of time to understand what is this thing running and to analyze everything, but let me make it shorter for you. So basically, the printer is running operating system called Tradex, and it's running over a chip, an ARM9 chip, a big Indian, if it's interesting to you, and it has several components like system and stuff, common libraries and tasks. For system, it has 2-stage bootloader and some networking libraries and stuff like that. And then it has a lot of common libraries, just common libraries, and then tasks. Now, tasks are the rough equivalent of processes we know from normal operating systems. And once we have this picture, it's pretty easy for us to say, okay, so these are the parts of the operating system that are using the fax functionality, and we should concentrate on those parts, right? And we can leave pretty much everything else aside. And that's nice. But just a second before we do that, we spot something that doesn't seem right. We see this. There's SpiderMonkey in there. I don't know if you're familiar with SpiderMonkey, but SpiderMonkey is the JavaScript implementation of Mozilla. And we were thinking to ourselves, wait, it's a printer. Why would it be using JavaScript? It makes absolutely no sense. It's not a client, and it doesn't have Node.js on it. So what's going on? Why is this thing running JavaScript? And we kind of were intrigued by this question, and we started, xrefing back to see where is this functionality used. And it turns out that the answer is simple. It's used in a feature called PAC, proxy auto-configuration. It's pretty common thing, right? And it kind of, auto-configures your proxy when you do when you connect to the network and stuff like that. And it's pretty nice. And the thing is that the top layer functionality of this thing was actually written by HP engineers. And when we're looking at this top layer functionality, we see this very interesting thing. You see, just when it begins, this whole PAC procedure, it connects to this domain, fakeurl1234.com. Now, it just connects to this domain and does nothing with it. I don't know why, maybe some kind of sanity test, that's my best guess at least, but that's exactly what it does. And the interesting thing here is, do you have any idea who owns this domain, fakeurl1234.com? It's not HP. If it was HP, I wouldn't be asking. Who? No. Not soft disk, I wish. No, not soft disk. Let me give you a hint. You all know him or seen him at least once. That's because it's me. The domain wasn't registered. Yeah. So I registered this domain for $5, and now every HP printer in the world is connecting to my domain. So good. When we told this to HP, amazingly they left as well, but maybe if they hear this now, we are willing to sell this for a very good price for HP. Okay, so let's go on with the fact story. So for that, I will give it over to Eyal.
Thank you. So after we finished messing around with SpiderMonkey, we decided to focus back on T30. T30, also known as ITU T recommendation T30, is a standard that defines the fax protocol. It's a huge PDF document, more than 300 pages, and defines all of the faces and messages we need in order to send and receive a fax. This standard was first designed on 1985 and was last updated more than a decade ago. So it's a very old standard. And that's good for us because we look for vulnerabilities in an old and complicated standard. That's great. While we read through the standard, we started to reverse engineer the T30 state machine in the firmware itself, and it looked like this. After we saw this graph view, we actually were kind of depressed. And after which we saw that this is a good graph view because most of the code blocks you can see over there contains additional functions with additional mini state machines inside them. So it's a really complex state machine. And if that wasn't enough, it turns out that the firmware heavily relies on function pointers and global variables. And it's going to be very complicated to statically reverse engineering this model. Usually, I prefer to statically reverse engineer firmware models. This time, we had to change tactics and go for a more dynamic approach. We'll need a debugger. But we have another challenge. How can we debug a printer? It's a box. It outputs pages. It's not used to debugging. So we have several challenges inside it. As Yaniv mentioned earlier, we had a JTAG and we have a serial port, but they weren't very useful. We then tried to search for a built-in GDB stub we could connect to and debug, and we couldn't find one either. At this point, we should remember that I can't simply load a debugger because I have no control over the execution flow. And another fact is that the printer uses a hardware watchdog. This watchdog will monitor the main CPU and will trigger a reboot whenever the CPU halts or enters an endless loop. Essentially, a breakpoint halts the program. So we can't simply use a debugger and issue some breakpoints because the watchdog will reboot the printer, and that won't be very useful. We decided to split up the challenges one by one. If you could find any vulnerability to execute our own code on the printer, we can try to use it to load a debugger for own. At this point of our research, we had a stroke of luck. And that's great because we believe usually that luck is a fundamental part of every research we do. And here we have our stroke of luck. On the 19th of July, Sandra published a vulnerability called Devil's Ivy. Devil's Ivy is a remote code execution vulnerability in the GSOAP open source. Embedded devices, and our printer included, tend to implement embedded web servers inside them used for management and configuration. And in our case, this web server used GSOAP. After further examination, we had a jackpot. It turns out that our printer is vulnerable to Devil's Ivy. We have a debugging vulnerability. We can continue on. So those of you who are not familiar with Devil's Ivy, here's the code, and here's a vulnerable snippet, decompiled. Unfortunate for us, Devil's Ivy is a signed integer underflow vulnerability. And it means we need to send roughly 2 gigabytes of data in order to achieve a stack-based buffer overflow. HP prides itself on the printing speed of the printers, not on the network speed of the printers. So we had several optimization rounds, and it took us 7 minutes for each exploit attempt. And this point signals the end of our stroke of luck because we soon found out that our exploit had several side effects, one of which is after each successful exploit attempt, we're going to have a grace period of 3 to 10 minutes, and then the printer crashes. And then we need to wait additional 7 minutes for one more exploit. So I had a lot of time to check out my Twitter account during the research. It's the only vulnerability we have. It's a remote code execution vulnerability. We can't be picky. Initially, we had several debugging challenges, but we wanted a debugger so we could read RAM and write RAM, so we could dynamically reverse engineer the firmware. Now that we have our vulnerability, Devil's Ivy, we can use it to load a debugger for own. Our debugger will need to be executed. We need to bypass several memory protections of the MPU. And the most important thing is that we want to connect to this debugger, and we want the printer to be okay. So we need to somehow blend our debugger in the address space of the firmware so the printer will behave correctly, and we will have an additional task with a debugger. We couldn't find any built-in known open source debugger that does it. And my brother usually tells me to not reinvent the wheel. and the wheel won't help me debug a printer, so we reinvented a debugger instead. So this is Scout. Scout is an instruction-based debugger. It currently supports Intel CPUs as well as ARM. It supports ARM's thumb mode because the printer uses it, so I had to implement it, and you get it as a bonus. In a previous research, we used a prototype version of Scout for Linux kernel research. So we compiled Scout as a kernel driver, we loaded it up, and debugged the kernel. This time we're going to use Scout in its embedded compilation mode. In this mode, you compile Scout to a fully position independent code, and I mean fully position independent. It has its own global offset table with addresses of useful firmware functions such as socket, bind, memcopy, or sleep, so we can find them in its own global offset table and call them. Once compiled, you've got a fully position independent blob. You simply inject it to the address space using a vulnerability and execute it. Being an instruction-based debugger, Scout will create a TCP server, wait for connections, and we can use Scout's Python agent to connect to the agent, to the server, send our instructions to read RAM, write RAM, show a picture on the screen of the printer, whatever function we implemented. You can find Scout in our GitHub account. It comes out with the Linux kernel driver, compilation scripts, tutorials, and everything you want. Now that we finally have a debugger, we can reach the most important thing of them all. We covered many topics during this talk. We haven't yet described to you how a fax actually works. Using Scout, we were able to dynamically reverse engineer the firmware. We learned how a fax actually works, and let me now describe it to you. In order to send a fax, we need a modem. We needed to send something to the receiver's modem. Our packets are going to be transferred to the main CPU to be handled in a T30 state machine. And later on, the data received will be processed and printed. When we start the connection between the two modems, we have several phases. In phase A, we have network interaction. We have probing and bridging. We have echo canceller and training. We have additional training, and it should be quite familiar to you. We don't have sound.
We don't have sound.
Yeah, it's the beeping sound you hear when you send faxes. These phases are used in order to create an HDLC tunnel. Over this tunnel, our T30 messages will be sent as HDLC datagrams from our modem to the receiver's modem. So now we can actually send T30 messages to be handled by the CPU. In T30, we have phase A, in which you send the caller ID, my phone number, or evil attacker, or whatever string you like. In phase B, we handshake capabilities, so we could support the best common capabilities for the faxes and distribution. Phase C is the most important phase. Here is actually send the data of a fax document. We send it line by line, page by page. And in phase D, we finish. I send ACK, I receive ACK, and we tear down the connection. Let us now see how a normal black and white fax document is going to be sent over the protocol. We have our document. It's going to be transferred over the HDLC tunnel, sent over phase C, and the final result will be this. We actually send data lines, which are the data of the TIFF file compressed in G3 or G4 compression of TIFF. If you think that something here is missing, then you're correct, because we have no header for the TIFF file. The printer itself auto-generates the header of the TIFF using data we send in phases A and B of the protocol. From an attacker's perspective, that's kind of bad news. TIFF parsers tend to have vulnerabilities, but usually you need to control the TIFF header to exploit them. And here we can only control the data itself. After we finish building up the TIFF, it's going to be sent for printing, because that's what normal people usually do with printers. T30, like any other protocol, supports many extensions, and that's where it becomes really interesting. Do you know what kind of extensions the T30 protocol supports? Well, it turns out that T30 supports color extension. Well, prior to this research, I didn't know that you can send the colorful fax. It turns out that the British DHS use it regularly to send high-quality documents of surgery between one hospital to another. They can use email. Let us now see how colorful fax is going to transfer of the protocol. We have our document over the HDLC tunnel, over phase C, and the final result is a JPEG file. This time we control the entire JPEG file, its headers and the data, because a colorful fax is essentially a JPEG file. And once received, it's going to be processed and printed. Now that we know how T30 works and how a fax works, where should we look for vulnerabilities inside it? Well, we have a very complex protocol with multiple layers, multiple decompressions, file formats, it exchanges strings, it has complex state machines, and essentially the easiest layer is the applicative one. We chose to use the JPEG parser for initial vulnerability research. We control the entire JPEG file. It's much better than the T file. Let us now see how JPEG looks like. So those of you who are not familiar with JPEG, here's a 101 discussion. JPEG consists of markers. You have a start of image, you have some marker with its length field and data, additional marker with its length field and data, additional marker, data, and an end of image marker. If we zoom in on one of these markers, we can see this. Our marker defines the 4x4 compression matrix. We have our markers opcode, length field, 4x4 compression matrix, and additional data. If we zoom in a bit deeper, we can see that we have a roughly sparse matrix. The values of the matrix are going to be accumulated into a length field, and in this case, it's 6. And using this length field, we know how much data we need to copy into a small local stock buffer. And in action, 6 bytes will be copied to the local stock buffer. And at this point, we were like, what a fax, because we control the entire marker. We can position large values in the matrix instead of being sparse. And we have 16 bytes going to be accumulated. It's going to be roughly 4 kilobytes. And 4 kilobytes of data will be copied to a small stock buffer at 256. And we have an overflow. We have a vulnerability in the trivial stack-based buffer overflow. We have no constraints over our bytes whatsoever. We can use non-ASCII bytes, null bytes, whatever byte we choose. 4 kilobytes of user control data is more than enough for initial loader, and this loader can later on read more data from the file we sent, the JPEG fax, and load whatever malware you want to the printer. When we exploit this vulnerability, we need to bypass several operating system security mitigations. Not really. It's a real-time operating system. It has a fixed address space, no ASLR, no NX bit, no stack canaries. It's an 80s party, it's cool, really easy to exploit. At this point, we contacted HP and had a responsible disclosure process. HP issued these 2 CVEs rated as critical with a CVSS score of 9.8. We actually flew over to HP to help them fix it, and HP initially told us to fly to Portland to help them, and I couldn't find any HP office in Portland. So we talked to them again, and they told Yaniv that I need to fly to Vancouver, and we were like, Vancouver is in Canada. And it turns out that we need to land in Portland, drive to Vancouver, Washington, and we helped them fix the vulnerabilities, patch them. So now it's fixed. If you were to Black Hat or saw HP's campaign, The Wolf, you know that HP prides itself on the security of its printers, and the security bulletin of these vulnerabilities states that more than 300 different printers models are affected, many millions of printers were updated. And we have an official response from HP. When HP learned of the issue, they worked quickly to provide updates to mitigate the risks. HP takes security seriously and encourages customers to keep the system updated to protect against potential vulnerabilities. And that's a good time for our demo.
Yeah, so this vulnerability is working on any HP OfficeJet printer. So if you have an OfficeJet printer at work or at home, probably you should update. And this is a short demo that we just made and filmed in the office. So excuse us for that. The exploit is actually pretty easy. You just buy a modem in $20 in Amazon, connect it, press enter, and then the fax is sent. And this is the receiving printer. It's receiving the fax. It takes some time, so we cut the frame here. And yeah, fax is received. And now the JPEG parsing is going on here, and basically, that's it. So, yeah, received. Okay, yeah, we have complete control over the printer. Now, that's not enough, because we wanted to show we can propagate to the network. So what we did is our fax actually included Eternal Blue in it. So once the printer is infected, it looks for devices connected to it, and if it finds it, it will just infect them, and you will see shortly a calc popping. So, yeah. Yeah, thank you. So we think it's pretty nice as well. And now some conclusions, and then we learn. So PSTN is still a valid attack vector in 2018, mind-blowing. Old and outdated protocols are probably bad for you, so try to stay away from them. And now what can you do? First, HP issued patches for that. So if you want, you can use this link and see if your printer is vulnerable, and then install the patches and so on and so forth. Then, you know, if you don't need fax, don't connect it. I mean, it comes with this cable out of the box. You don't really need to connect it. But if you do need to connect it, then maybe, you know, segregate your printers so that if they will be attacked, at least nobody will be able to propagate to the network and the attack will be confined. And now, these are all pretty good advices, but really, today, the best advice I can give you is please stop using fax. And now I'll just finish, and just before I do, I need to mention some friends who really helped us along the way. They helped us technically, physically, mentally, and they deserve some credit for that. So those are the guys, and one special guy and I who helped us a lot with this thing. And that's it. You can follow us on Twitter and read out more of our stuff on our blog. And thank you very much.
We went a bit... Fantastic work. We went a bit over time here. I think it was well worth it. Let's see 2 questions, and then we break for coffee, which will be a short coffee break. All 0 questions?
Over there.
Everything was clear.
Who paid for your fun?
Who paid?
Who paid for your fun?
Our
so
employer.
You did this research over, I guess, a period of time.
Yes.
And yeah.
We have an employer that pays us to do these things for some reason.
Great.
A lot of these big embedded devices use a software update aggregator or service. Does HP want to use one of these? That's what I thought your URL might be originally, was like a place for pushing firmware upgrades.
A software aggregator? What do you mean?
So like there are these services, I can't think of one off the top of my head because I'm tired, but there are these services that help you do upgrades. So HP would hire them, and they would cache a lot of firmwares around the world and push them to the devices.
They use no such thing. The FTP sites that you saw, the printer actually connects to this FTP site, download this file, and just does everything on its own. There's nothing.
For a couple million printers, or a couple 100 million printers?
I can tell you exactly how many, because they connect to my...
Bravo.
When they issued the patch, the FTP site fell down because millions of printers contacted it to download a few megabytes of firmware.
All right, I think that's a very good place to end this fantastic talk.
So what are you going to do with the IP addresses of printers connecting to you? Are you going to share that for cleaning up? Because I think they are not being software updated.
It's completely responsible. I'm doing nothing with it. The domain is there, but we are doing nothing with it.
No, but you could help in cleaning up.
I can help them. I can sell it. I can do a lot of things, but it's just a joke. We're doing nothing with it.